Welcome friends. Now let us study the applications of Gauss theorem. There are so many applications. First one is line charge, second one is sheet, third one is sphere. In sphere we have two cases, one is hollow, another one is solid. Okay, let us study the first one, line charge. Okay, so what will happen? There is a wire like this, conducting wire like a line. Okay, if you distribute the charge, they will distribute like this. Okay, all of you already studied how they will distribute. So now if I want to find out my electric field at this point P at a distance r. Okay, so what is the Gauss theorem suggests us? First we have to enclose this one with a closed surface. Let us take an example. In a wire, conducting wire, the copper wire is present inside, and over which we are giving a coating of plastic, and that coating, if you see the broad section, and that is cylindrical in nature. So as this is a line, so we will enclose with a closed surface with a same distance. Let it be a cylinder. Okay, let us see this pen. This pen is having a conducting wire, a refill inside, and to this refill the coating over which is given is which kind of structure? Is a cylindrical structure. So no doubt ever which. Okay, so we are using the wires inside, that one is copper wire is present, and to the copper wire the plastic wire coating is given. Okay, and that structure is cylindrical in nature, and this one is the broader section, right? Let us make like this. Clear? And what is our aim? Our aim is to find out what should be the electric field present here at this point due to this line charge, or what is the effect of this line charge on a point present here, right? Now, okay, so now let us solve it. Okay, the first part is over. We have to enclose with a closed surface. We have enclosed it, right? Now see, where is the electric field? The electric field is having a direction like this, or you can say in this direction also. Let us take one direction like this. This is my electric field. Okay, now let's take this curved areas area. Okay, the curved areas area, this is a curved area, this is cylinder like this. Okay, this is cylinder, and in this cylinders, this section is known as curved area. Okay, and this curved surface area is having a area vector this side. Okay, so E vector and A vector, how much degree they are making? 0 degree. So what is cos 0 degree? 1, right? Okay, so for the chord one, if we will calculate the flux, total flux, first one is, we will integrate, there is not a only a small section. Okay, this is a broad section, but we will take small sections. So if you take the small sections, you will have to integrate. Okay, so integration of E vector dot ds vector of the curved surface. Okay, and this is cos how much degree? 0 degree, plus another two surfaces are present. What are these? This top surface, bottom surface. Okay, let us check the bottom surface here. The bottom surface area vector is like this, but where the electric field lines are going? Like this. How much angle they are making? They are making 90 degree. So what is cos 90 degree? 0. Okay, so simply we will write integration of bottom E vector dot ds vector cos 90 degree. Okay, another one is for the top surface. The top surface also same. The top surface area vector is like this area vector, and the electric field is like this, so they will make 90 degree. So cos 90 degree is again 0. This is 0 and 0. So there is no flux in the top and bottom surface. So where you will get the flux? Only at the curved surface. So what is the answer? E integration of ds. Okay, so what is integration of ds of a curved surface of a cylinder? You know it very well. What is the formula? A into 2 pi r l, right? Now what is the third step? Second step you have done. Second step is equation formation of the flux. Equation formation of the flux. Now what is the third step? The third step is you have to compare with Gauss equation. You have to compare with the Gauss equation. Comparing with Gauss equation, right? So we will write E into 2 pi RL, and what is the Gauss equations? Flux formula Q by epsilon naught, right? Okay. As this is a line charge distribution, you will get your line charge density lambda is equal to charge upon unit length. So what is your Q? Q is nothing but lambda into L. Lambda into L, right? So what the equation we got before? E into 2 pi RL is equal to Q by epsilon naught. Let us place the value, that is E into 2 pi RL. Let us place this Q value here, that is equal to lambda L by epsilon naught. Okay, so after solving, what we need? Electric field only. This we need lambda by epsilon naught 2 pi r. Okay, and this L and this L is being cancelled, right? So what is the answer? E equal to lambda by 2 pi epsilon naught r. Clear everyone? Okay, so this much if you will derive, you will get the 3 marks. Now let us see what will happen on a sheet. Okay, you'll draw a structure like this. Okay, and the charges are being distributed, you know it very well, in a sheet like this. Okay, so what is the next step? We need to find out at a distance r from the sheet what should be the electric field at this point P. So what is the first step? You have to enclose with a closed surface or Gaussian surface. Again I can enclose with a cylinder. So we can make this side also is having the same distance r. Okay, that means the structure should be same. The structure of the cylinder in both the side should be same. The symmetry should be same. Here also you can take the cylinder, because this to this I have considered as a line. Okay, this section. So how to enclose a line charge? Again with a cylinder, right? Any of the method you can use. This method is being used before. Okay, so now let us see the curved surface. The cylinder's curved surface is this one, is having a area vector like this, and where the electric field is like this. How much angle they are making? 90 degree. So 90 degree means cos 90 degree equal to 0. So there should be no flux in the curved surface. But let us see the flat 1 and flat 2. Let us name it. This is flat 1, flat surface 1. This is flat surface 2. Okay. So here you can observe your area vector is like this, your electric field also like this. So how much degree they are making? 0 degree. What is cos 0 degree? 1. So you will get your flux. This side also same, area vector like this, electric field like this. So cos 0 degree equal to 1. You will get your answer. Now let us see the full note on sheet, that is infinite plane sheet. The flux linked with the closed surface, we need to find out the flux formula. Phi equal to, how many surfaces are there? Integration of curved surface, flat surface 1 and flat surface 2, EDS cos theta, EDS cos theta, EDS cos theta. Now at curved surface, field line is making how much degree? 90 degree. Here is the curved surface 90 degree, so no flux, so that's why 0. Plus you will get only the answer at flat surface 1 and flat surface 2. So E, if you take outside, what is integration of ds? Is s, and this one is what? Cos 0 degree. So cos 0 degree is 1. So that's why I have not mentioned. So Es plus Es equal to 2Es. So we know here, like line charge density, here surface charge density is present. So what is surface charge density? Sigma is equal to Q upon S, that is charge upon unit surface. So what is charge? Equal to sigma into S. So now what is the third step? The third step is comparing with the Gauss equation. Compare. Okay. So what is the Gauss equation? Close integration of E vector dot ds vector equal to Q by epsilon naught. This is the Gauss equation. Now compare. What answer you got? 2Es, flux formula, flux you got 2Es. Now compare with your another flux formula. What is the flux formula here? Phi for the Gauss equation, Q by epsilon naught. Okay, instead of Q I have already placed sigma into S divided by epsilon naught. So what is our job? To find out electric field. So electric field equal to sigma by 2 into epsilon naught. Okay, this 2 will go this side. So E equal to sigma by 2 into epsilon naught. So this is for what? For a sheet, right? So this is the full note.